Hello everyone, here is our fourth installment this week and we're looking at redox stoichiometry. Now with redox stoichiometry, and don't be intimidated by the word stoichiometry, this is just about looking at ratios, it's no big deal. But the key thing with stoich is balanced reactions, and we get to revisit two formulas from your past. So if you look at the two that are here, the key thing is for both of those, we have a N, which is number of moles. It's an amount. And just to remind you about units for each of these, N is always in mole, of course. Little m stands for mass in grams. That big M is your molar mass, grams per mole. And going back to the bottom one, C here is your concentration. And remember, concentration is a molar concentration here. It's always in moles per liter, which means the volume has to be in liters. If it's written in milliliters, for example, or in kiloliters, you're going to have to convert it to liters to use this. And again, I'll stress it. This is how this relates into what we've been doing. Stoichiometry means we need balance. So we need a balanced reaction. Okay, just a quick reminder, this is total review from Chem 20, the stoichiometric process. And let me say it again, the reaction has to be balanced. Key thing, guys. Now remember that you're going to use the info to figure out and to compare the number of moles. And number of moles, of course, is related to N, hence going back to those two formulas from before. How do you do that? Look at the coefficients of the balanced chemical reaction and look at the molar ratio, which I will review with you momentarily. You're probably going to have to do an extra step and either go from the mass or calculate the mass, or go from a concentration or calculate a concentration. Either way, this is going to relate back to steps 2 and steps 3. All right, folks, you can go back and look at that as often as you need. It's in the printed notes. Let's jump to a question and actually put this into practice. So when you're reading through these, make sure you're being careful about what you're actually given. For instance, we have a volume and we have a number in moles per liter. While volume, of course, is V, moles per liter, you've been given a concentration here. Now, key thing is that both of those relate directly to potassium dichromate. And this potassium dichromate's been acidified. These are all pretty big deals. Hey, whenever you see the word acidified, that means that H plus is going to be an option for you to use. And anytime we've got a solution, which includes acids, you know that water is going to be an option. Potassium dichromate is an ionic compound, so we've got K plus present, and dichromate Cr2O7 2 negative, of course, is present as well. All these things have to be accounted for. Keep on going. We're dealing with the oxidization of another different value in grams, take note of the grams, and another substance, nickel. So for this scenario, if it's in grams, we've been given a mass, and nickel, of course, is going to be nickel solid. But pay attention. What I put here in yellow applies to potassium dichromate. What I put here in green applies to nickel. Make sure that you're not getting different things mixed up. All right, let's keep going. How are you going to write a balanced reaction here? I don't give you a reaction. This goes back to last week's lessons where you need to take note of absolutely everything that's present. And in this situation, we have H plus aqueous present because it's acidified. We have liquid water because we have solutions and we have an acid. We have potassium dichromate, so you split that up. It's an ionic compound. Remember, they dissociate. K plus aqueous, dichromate, the Cr2O7 2 negative aqueous, and last but not least, our solid nickel. Ultimately, if we're going to make this into a balanced redox reaction, we have to figure out what the strongest oxidizing agent is and what the strongest reducing agent, which means you're going back to your data booklet. All right, check out your chart. And when we look through this, we're going to start at the top up here and start scanning down, looking for our strongest oxidizing agent. And when you do that, you come across it fairly quickly. It's right here, right? There's that dichromate with the acidified, so I can use that 14H plus. There's my SOA. Vice versa, we're going to go from the bottom down here and work our way up to look for the SRA. So same thing, start scanning, work your way through, and it doesn't take too long until we find, I'm trying to highlight nickel there, right about there, right? And now we've got our SRA. Okay, going back. Take those two. Our SOA, of course, is going to be our reduction reaction. So the gain in electrons. In this case, we have Cr2O7, 2 negative aqueous, being added to, take right from the chart, guys. So we're going back, reviewing an old technique. 14H plus, and this is that reduction, of course, so we're going to add in our 6 electrons to produce 2 chromium, 3 plus aqueous, plus 7H2O liquid. Vice versa, our SRA, or our oxidation reaction, this is going to be the nickel. Remember to write it as an oxidation, as losing electrons. So the nickel solid is going to produce our nickel 2 plus aqueous, again, right off the table, plus our 2 electrons. All right, taking a step back, look at those electrons. We have 6 electrons being gained, 2 electrons being lost, and we figure that out by correctly identifying that our SOA was H plus and dichromate. And we figure that out by figuring out that our nickel is going to be our SRA. So next step is make sure those are balanced. Take those 2 electrons times that entire reaction by 3. That means that in the end, our net balanced reaction, and I'm actually going to put this onto the next page, guys, so that we can keep on working at it. But consider what's happening here, right? We've got our dichromate reacting with the 14H plus, and then we've got the nickel reaction we had to times by 3, so that we can balance out those electrons. Here we go. Redox. Cr2O7, 2 negative aqueous, plus those same 14H plus. Now take note, 3 nickel solid is going to produce 2 Cr3 plus aqueous, plus those same 7 waters. And now this has to be multiplied by 3 as well. 3 Ni, 2 plus aqueous. Oh wait, here comes the stoichiometry. Look back to the question, look back what's been given to you and what the purpose of the question is. We're trying to find the volume of the dichromate. That's the whole purpose. Now, yes, it's of the potassium dichromate, but that's still your dichromate solution. Don't forget, you've been given in the original question a concentration for that. It was 0.225 moles per liter. Okay? Volume, concentration, and think about those for a second. We're looking for volume. We have concentration. Remember the formula that goes with that. Okay, skip over to nickel because we have some information about that too. We were told originally that the mass of nickel is equal to 5.00 grams. Now here we actually have enough information to get our number of moles because molar mass is something that's available, of course, on your periodic table. Molar mass of nickel is 58.69 grams per mole. So go back to your formulas, those ones that I reintroduced you to, and we know that N is equal to mass over molar mass. Okay, if we've got mass over molar mass, we've got 5.00 grams divided by 58.69 grams per mole. Okay, grams are going to cancel out, and my number of moles of nickel. Sorry, I'm having a hard time writing neatly here. So make sure you have the other notes in front of you if you need to. That can help. We get 0.08519 ... moles. Again, that's the number of moles of our nickel. Okay, I cannot get my volume back of the dichromate unless I also have N for that dichromate, right? But N of dichromate, the only way we're going to get that is by recognizing that we need this balanced chemical reaction. And then look at the ratio of the nickel to the dichromate. So take this, and I'm not sure if all of you did it this way when you were in Chem 20, but this is what I often show, is you can go back to what's on where you're starting, this 3, and think about where you're going to the dichromate, which is a 1, even though it's not written there, and recognize if we're going from nickel to dichromate, the way we're going to do that is take this number and we're going to divide it by 3, and then times by, well, in this case, 1. And that'll get us to our number of moles of that dichromate, okay? Which, when you go through that process, you get 0.02839. It keeps on going, ... moles. Consider what's happening here. Ultimately, we're just looking at the ratio of the number of moles of nickel compared to the number of moles of that dichromate, Cr2O7, 2 negative. And when we compare the moles of one to the other, it's a 3 mole versus 1 mole ratio. Okay, so 3 to 1 ratio, and I already know how many moles of nickel I've got. So I'm going to have 1/3 of that of the dichromate. In other words, divide by 3 times by 1. Okay, let's jump back. Think back to formulas. If N is equal to C times V, then that means that V is going to be equal to N over C. We're getting really close to an end answer here. Equals 0.02839 ... moles divided by my concentration that I was given in the question, 0.225 moles per liter. Always pay attention to what units are doing right here, guys. Like moles are canceling out. We're left with liters. That makes sense. Even when we did molar mass over here, right? The grams of the mass canceled out with the grams of the molar mass, leaving us with moles. It all works out. Okay, total volume equals, and go back to the original question. Remember, we're dealing with 3 sig digs. We have 0.126 liters. And there we have it. Stoichiometry with redox reactions. As long as you balance the redox reaction first, we're good to go. All right, let's try another one, which is going to review the new type of balancing that we've been doing. So when you consider this one, we have our 16.50 gram piece of zinc solid placed in a 300 mils. So again, start thinking about numbers here, right? This is the mass of zinc. Yellow goes with yellow. Then we keep going. I have 300 mils of this concentration of chromate. So green goes with green. I've got a volume, I've got a concentration of my chromate, sorry. The whole purpose of the question, and here's where things get a little bit sticky. Calculate the mass of zinc that remains at the end of the reaction. Okay, think carefully about what's going on. So in other words, this mass at the beginning is actually an initial mass, right? That's that starting mass of zinc. It's not what we finish off with. And we want to know what mass is left over. We're looking for final mass, if you will. Which again, complicates things a bit. All right, in your worksheet, you have the beginning of this reaction. So let's start with that and then keep going from there. So this is already in your notes. Zinc solid is going to react with the chromate. And honestly, if we were doing this in class, guys, I wouldn't have given you these. I'm just trying to help you out because you're trying to do it at home on your own. And then we've got zinc 2 plus aqueous plus chromium Cr3 plus aqueous. Okay, here's what we start with. Now, when you're looking at what's occurring, our step one, if we have a reaction, is that we can take this and recognize our oxidation numbers. Zinc starts at 0. Oxygen is -2. 4 times -2 is -8. I need still -2 left over, so that's going to make my chromium a +6. Keep on going. Zinc is at +2, and then this chromium is at +3. Now I'm choosing to balance this one with oxidation numbers. You could also split this up into 2 half reactions. That would work too. There's a couple assumptions that you can make in order to do this properly. The first thing that you can assume is that this is acidic conditions, which means then that you can assume that we can add H plus where we need it, and we can add liquid water where we need it. So keep those two things in mind. All right, keep on going. Check out what's happening from an oxidation number perspective. To go from 0 to +2, this is going to lose 2 electrons. For our chromium, to go from +6 all the way to +3, it's going to gain 3 electrons. Now this is per an atom, but the good news is there's 1 zinc reacting, 1 zinc being produced, 1 chromium reacting, 1 chromium being produced, so that makes this pretty nice and easy. Now we have to balance out those electrons. If it loses 2, I need a total of 6 times 3, 6 electrons lost. Vice versa, if it gains 3, I'm going to times that by 2, which will give me my 6 electrons gained. We now have a situation where we balanced our lost electrons with our gained electrons by making sure that we multiply the zinc as the reducing agent by 3 and multiplying the chromate as the oxidizing agent by 2. All right, I'm going to jump over to the next page to actually write this balanced reaction. Here we go. Okay, all we have at this point is our zinc solid, which I stated we're going to have to multiply by 3. Next thing we have is, because we're adding these together, don't forget, our chromate, Cr042 negative, aqueous, and this one we had to multiply by 2. Okay, leave some space, because we're going to have to balance out those oxygens and those waters. Keep going. I've got my zinc 2 plus aqueous, which again I had to multiply by 3 to balance out those zinc atoms. And I've got my Cr3 plus aqueous, which again I'm going to have to multiply by 2 to balance out that chromium. Now we're going to have to figure out our waters and our hydrogens with those oxygens and hydrogens. So we have a total of 8 oxygens on the left-hand side reacting, which means I'm going to need to add a total of 8 waters over here to balance that out. Now, if I added my 8 waters, I've got 16 hydrogens there now, which means I'm going to have to go back over here and add 16 hydrogens to balance that out. Okay. So far, so good. I know it's a little hard to read. My pen on the iPad has issues, but look to my notes, the PDF ones, to help you. They're nice and neat. Okay, look back to the question. What do you actually know? Well, you know an original mass of zinc, which is 16.50 grams. We also always know the molar masses of our known chemicals. Molar mass of zinc is 65.41 grams per mole. Now, don't jump and suddenly start doing your N, because keep in mind, this mass that you just wrote down is actually the initial mass. It's not how much reacted, so be careful. We know that some of that's going to be left over. Remember at the question, how much remains? So that entire 16.50 grams doesn't completely react. Take your time, think through questions, be careful. Okay, go back to the chromate. numbers that were given to you. This is a volume of 300 mils. Now, it can't be left in mils. We're going to have to change this to liters, divide by 1,000, 0.300 liters. And the concentration of this one is given 0.475 moles per liter. Okay, that's more than enough information to figure out what our N is for the chromate. And then we can use the balanced reaction. N here is equal to C times V. When you multiply C and V together, and guys, you need to plug these in with units. I'm not going to right here because my pen's just being wonky, but take the 0.475 moles per liter times by the 0.300 liters. You're going to get a total, don't round it, 0.1425 moles, because we need to use this again. Consider what's happening here. This is your N, your amount of chromate, but I can use the balanced chemical reaction to then figure out my N for my zinc. Okay, look at those numbers. I've got a 2 and a 3. So first step with the ratio is divide by 2. Divide by 2. Second step with the ratio then is times by 3. So literally take on your calculator, 0.1425 divided by 2. Then get that answer and times it by 3. Use the mole ratio to help you. And when you go through that, you're going to get an N equal to 0.21375 moles. Now here's where we can actually do a calculation. This N can be used with the molar mass to figure out what mass actually reacted. Because remember, that 16.50 is the mass we started with, not how much reacted. Okay. Rearrange that formula, and M is equal to N, the number of moles, times the molar mass. We're going to take that 0.21375 moles times by the molar mass, 65.41 grams per mole. Moles cancel out. We're going to be left with a mass. And the mass of that zinc is going to be equal to, again, don't round yet, 13.9813 grams. Once again, this is not an end answer, guys. So if you think back, that 16.5 grams was your initial mass. That's what you started with. Vice versa, this here, this 13.9815, this is our reacted mass. How much actually reacted with the chromate. We need the final mass. We need to know how much of this is left over. How do you do that? Well, you're going to take the initial mass and you're going to minus the mass that reacted, and that'll give us our final mass. Initial mass was 16.50 grams. Subtract the one you just figured out, 13.98 grams. We end up with a final mass of our zinc of 2.52 grams. 3 sig digs, there it is, done and done. Again, I highly recommend have another look at the actual notes that are printed out, or that are, posted for you, the PDF, and see if that helps you out. Okay, homework, guys. You should be at the point now where you complete both 5 and 6 from your assignment, and we're getting close to the end. There's one more podcast this week on titrations and one more question on your assignment. Always let me know if you got questions.